Okay guys, this is ME 696 graduate course linear system theory, and we are dealing with the rigorous mathematics. Okay, so, and I try to teach you also MATLAB based of this, because I do believe that if you don't know rigorous math, and more importantly, if you don't know how to implement in reality, you are not engineer. You are either mathematician or you are, I don't know, a blind engineer. Okay, so you have to know the both of them. This is my belief in the control system. Okay, so in the linear systems theory, why I do believe that you have to know how to implement in reality, because I have a dynamic system and control lab that maybe you have seen, DSCL. And when it comes that we want to implement a controller, non-linear controller, linear controller, let me show you. The real robots, in particular in high degree of freedom robots, I and my research group, my doctoral students, PhD students, and the master students, they see that there are lots of difficulties. We have to modify the purely theoretical controllers and approaches to be implemented to the real robots. You get what I mean? So let me close the window because there are lots of noise and lots of the noisy people here. Come on. Where is that? Okay. Okay guys, so you see that we have lots of the robot in this lab, and we had lots of difficult time. I mean that my research group, that my PhD students, to implement the purely developed mathematical controllers to the reality. So you have to know how to implement that in the reality. At least you have to know how to code in the MATLAB. Okay, the era of that you developed lots of mathematics and leave it there and without any experimental validation, or at least the simulation, is over. So you have to know this. Okay, linear system theory. So as the name says, that we want to control that the linear systems, we want to control linear control systems, or it's proper that I say dynamic systems. Okay, when I'm talking about the dynamics, means that I'm talking about the differential equation, differential equations. Okay, so we have two types of the equations. They have the linear and they are non-linear equations. Okay, so the famous example that I'm teaching in all my classes, from dynamics to vibration to undergraduate control to robotics, is the pendulum example. That has a link, and the particle mass is here. That's right. So I'm skipping how I drive that because it's the class of the controllers, not class of dynamics or vibration robotics. I hope that you know it because you're graduate students. That's right. So if the angular theta, okay, and if I apply a control torque here, tau, you have two types of the equation from this. One of them is written as theta double dot, angular acceleration, plus gravity over length of that pendulum, sine of theta is equal to tau over L. That's right. Another is theta double dot. After linearization, sorry guys, this is linear version, and this is non-linear. This is linearized version of this. That's right. This is linearized version of this. G over L sine of theta is equal to tau over L. So I linearize this nonlinear equation, differential equation, which is ordinary differential equation, is not partial differential equation. We are talking about the ordinary or denary differential equations, not partial differential equations. Okay, so we are linearizing this and we get this. That's right. Understand? So now we are controlling this system in this course specifically. Linear ordinary differential equations. Okay, like what? Like where is that? Like I don't know, x double dot plus 2x dot plus 4x is equal to u1. This is the control input that we're gonna design together through this course. Or I don't know, you have two spring and mass and dampers that they are acting in the series. You're gonna have x double dot 1, 2x double dot 1 plus 4x dot 1 minus x dot 2 plus I don't know 4 x1 minus x2 is equal to f1. That I suppose that you learned this in the vibration course. Or 3x double dot 1 x double dot 2 plus 3x dot 2 minus x dot 1 let me make this 4 plus I don't know 5x2 is equal to f2. That's right. So these are a set of the ordinary differential equation, because the coefficients of these differential equations, they are constant. That's right. And the order of these time derivatives are 1. Okay. So when I say that the coefficients of this differential equation is constant, means that we are dealing with this kind of equation, specifically in this course. Linear time invariant systems. Time invariant systems means that the coefficients are not functions of the time. So, and this is a linear differential equation. So this is also a linear, this is also time invariant systems. That's right, because the coefficients are constant of constant, but this is non-linear time invariant system. So if you want to fit this equation into this course, you have to linearize it first. Understand? So before going deep into the mathematics, let me remind you a few things. First of all, if you have, I hope that you know from the previous courses, undergraduate courses, for linearization of, say, x double dot plus sine of x plus sine of now let me do like this. X dot, make it simple, plus sine of x cosine of x, that's right, is equal to 0. Understand? So I'm asking you linearize this differential equation. Okay. But the first question, as you as graduate of the mechanical engineering, is that around what point I have to linearize? Around what? My answer gonna be equilibrium point. For those of you who don't know, or you forgot that, equilibrium point simply means a point that if you leave system without applying any external force, it's gonna remain there forever and gonna be stable. That's right. So even that you have, suppose you have a force at the equation originally has such a external force here. So when I ask you, please find the equilibrium point of the system, means that you have to remove the external force from the system. So you have to do this sine of x, and the cosine of x is equal to 0. Based on my definition, I told you equilibrium point is a point that system remains remains at rest. Physically means system has no velocity, has no acceleration. So I'm going to say bye-bye to the velocity and the bye-bye to the acceleration to find the equilibrium point. And from trigonometry, we know that sine of 2x is equal to 2 sine x and the cosine x, remember? So simply you from here you can say sine of x cosine of x is equal to 1 over 2 sine of 2x. So on the other hand, you can say from here that 1 over 2 sine of 2x is 0. I am trying to find the equilibrium point of the system. Why? Because I want to linearize this nonlinear time invariant differential equation to linear time invariant differential equation. Clear? Okay. So we know that from mathematics that this is sine of k pi from trigonometry. Okay, that's right. And the k is 0, plus minus 1, plus minus 2, and this. With respect to the system configuration, dynamical configuration, you can judge which of this number gives you the equilibrium point. You have to judge it about the stability of the system and stability of the system. Okay, suppose, so on the other hand, we get here 2x is equal to k pi, that's right, from this equality. So you get that the equilibrium point that we are showing with x hat gonna be k pi over 2. So by giving that first, you're gonna have the first. So first of all, you have to know that a system given has multiple equilibrium points. This is your function as control engineer to judge which of them is a right answer. This is your function. Okay. K0 gives equilibrium point of 0 here. This x dot is, for giving 1, gonna be pi over 2, right? And forever. Suppose, only suppose that I know from the, I don't know what's the equation of this, I don't know which system it is, but suppose I know that, I'm going to teach you later, this is the equilibrium point of the system. By having that, using the Taylor series expansion, okay, that if you have a nonlinear term, you can linearize around the equilibrium point of that system plus round f over round x at the equilibrium point of the system, x minus x star plus round in 1 factorial f over 2 factorial round x square x to x star x minus x star square plus forever. That's right. So but after this sucks. Why? Because we linearizing the system. We need the order of the 1, not order of 2 or order of 3. You understand what I'm talking about? So by having this, and we know the current point of the system is 0, so now I can linearize this term. Understand? So this is our equation, x double dot plus x dot plus sine of x and the cosine of x is f. Why? Because we want to make this system to be fit in the topic of this course, LTI systems, linear time invariant. System now is time invariant because the coefficients are 1, but it's not linear. That's right. Clear, guys? So now after finding that, I'm gonna say, I hope that you know, sine of x is equal to, based on the Taylor series expansion, sine of 0 equilibrium point based on this formula. First derivative with respect to the x, sine first derivative gonna be what? Cosine of x. At where? At 0. In x minus x naught. This is 0 at 0. And this is 1, so you can say sine of x is equal to x. And the cosine of x, if you do the same, you're going to have cosine of 0 minus sine of x after first time derivative, x minus 0. This is 0 because sine of 0 is 0. The answer is 1. Understand? So you can say around the equilibrium point, sine of x, cosine of x can be approximated as x. Around the equilibrium point. I'm emphasizing around the equilibrium point. Now you're gonna tell me, Payman, you know what? I'm gonna take this as the term too. So you're gonna say sine of x, cosine of x is equal to sine of 0, cosine of 0 plus cosine of x in minus sine of x, first time derivative. I'm sorry. So it's gonna be cosine of x square minus sine of x square. Sorry, derivative of first and second plus first in this, where at x0. X minus, again this. Obviously this is 0. If you put x0 is 1 here in x, again you get the same result. It doesn't matter that you go 1 by 1 here. Okay, so it is almost the same result. So now I am transferring this time invariant but non-linear ordinary differential equation to what? To LTI system. So x double dot plus x dot plus x is equal to f. So now you have LTI system, guys. Right? Understand? Is recording? Okay. Understand? This is another approach, guys, for linearization that we name it as Jacobian metrics in control. Jacobian metrics, guys. Jacobian metrics. That you have to wait a little because I have to teach you a few things. So the question is, fundamental question is, why I have to change a nonlinear time invariant differential equation to a linear time? Because at the end of the day in this course, I'm going to take you back to undergraduate control. You have to use Laplace transform. Okay, because when you are dealing with the linear differential equation, you can implement the Laplace transform. Understand what I'm talking about? So now let's go for refreshing your mind. This equation, if I apply the Laplace transform, by the way, if you forgot, Laplace of a given function f of t, which is f of s, it is 0 to infinity e minus st f of t and dt, and the s is what, you know from the undergraduate, j omega. J is the complex number, root square of -1, and this is the frequency, not natural frequency, not natural frequency. This is excitation frequency. Okay, as you have seen in the body plot in undergraduate control and these kind of things. So if I apply a Laplace transform to the both sides of this equation by assuming that the initial conditions are 0, or refreshing your mind, you know that the x double dot, when it comes to the S domain or frequency domain, you're going to have s square x of s, so plus s x of s plus x of s is equal to f of s. So the Laplace transform, for refreshing your mind, is a bridge that we can come from the time domain to frequency domain. So from here you can find the transfer function. Remember, output over input. This is external force as input of your system. Like what? When you are pushing the gas pedal in your car, this is the input of the system. You are controlling the position of your car, or velocity of your car, or acceleration of your car. And the output gonna be velocity, acceleration, or the position of your car. It's gonna be here 1 over s squared plus s plus 1. And that's why you want to make our nonlinear time invariant differential equation to what? Linear time invariant differential equations. In this course, specifically in this course, I'm emphasizing. Okay? So, now after knowing that we are working on the differential time invariant linear differential equations, so in this course we're gonna focus on state space representations of transfer function systems. These are the fundamentals that you have to know. Okay, we have 4 state space representation of transfer function system. For those of you that you don't know what is state space, first let me teach you or refresh your mind. Okay, so look at the previous example that we linearized. That's right, is equal to x is equal to f. Okay, this is how we generate state space, state variables, and then state space equations. How? We say, you know what? I'm gonna say m is equal to m1 is equal to the position of your system. This is how we define it. And the m2 is the velocity of the system. When I say position and velocity, don't stick to that forever. It can be, m1 can be pressure of a tank, m2 can be rate of pressure of a tank, time derivative of that. m1 can be temperature of a room, m2 can be rate of temperature of a room. m1 can be length of a macaroni that you are eating, m2 can be rate of velocity of macaroni that you are eating and going to your mouth. So it is for any system. Okay, you understand? So if I have time derivative from both sides of these, you get m dot is equal to, so you have, hold on, there is a blotch here. I'm going to stop. Okay, so it was a It was so you're gonna have x dot, okay, is equal to, why it's stopping? Okay, now it's fixed. The pen has some. So m dot 1 is equal to x dot. That's right. See from this line. So x dot is, as I defined, is how much? Is m2. And now from this line, m dot 2 is equal to x double dot, because time derivative of velocity gives the acceleration. But you can find this x double dot from this equation. Get here? X double dot is f minus x dot. So it is f minus, what is x state variable? Is m1. What is x dot? Is m2. Here we go. So m1 and m2 are named state variables. So m2 gonna be, from here gonna be f minus, oh, I don't know, f minus m1 minus m2. So your state space equations or state space representation is m dot 1 is equal to m2 and m dot 2 is equal to f minus m1 minus m2. And this is exactly the form that MATLAB understands. You can solve your differential equation, or you can implement controller inside this state space form that I'm gonna go over that soon on MATLAB like this. Understand what I'm talking about? So it's very interesting. So this is state space representation. Okay? So let me do another example. Then go to transfer functions. So suppose I have this equation, x double dot plus x dot sine of x plus x cosine of x sine of x is equal to u. That you in this course, you learn how to design this for LTI system. This is control input, like as your leg on the gas pedal. Okay, understand? First of all, this is time invariant system, but the problem is that you have to linearize it. Let's say, as I taught you, x dot is 0. X dot, I mean the equilibrium point. So you can say this is x. You can say this as 1, and this is x. That's right. So first of all, if you do that, you get this x dot plus x square is equal to u. Okay, is this LTI system? What's the answer? 10 seconds. Look at the equation. Obviously it's not. It's still nonlinear time invariant system. So you're gonna say, what I have to do with this? Okay, let us just examine this, huh? Let us just examine this. Or this, for simplicity. So I want to say x2 almost is f at 0, means x2 at 0 at equilibrium point, plus first time derivative 2x at equilibrium point of 0 and x minus x naught. This is 0 obviously, and this is 0, so you have to say it is 0. So you have to eliminate from this. Understand? So what about this, guys? I'm giving you 1 minute that you saw. I know the answer. Don't go forward in the video. You do it, okay? 1 minute from now. Let me pause it. Save time. Okay guys, so it is very clear. That's right. This can also must be 0. That's right. This must be also 0. So your LTI system from the above equation gonna be U. That's right. This is the simplest model of your car. Very, very simple model of your car. Can be. Okay, not is that like that. So having that, so you can say m.1 again is m2. The state space equations. m.2 is equal to what? Obviously U. This is your state space equations. Another example. So you say x double dot plus x dot cosine of x plus sine of x is equal to U. This is another example. Now using the Taylor series expansion, by assuming that x dot is the current point is 0, okay, which is 0 if you do that as I did for this equation, so it can be 0, I mean. So it is gonna be 1, this is gonna be x, so you have x double dot plus x dot plus x is equal to U. So the state space equation gonna be m double dot 1 is m2 and m double dot 2 is U. Understand? So now after knowing this, let me go to this topic. So we know what is the state space representation of transfer function systems. Okay, so guys, if you have look at here guys, in the previous example the highest order of the time derivative was 2, but you can have this system in reality guys. This system, let me plot it for you. You can have a spring, one mass, spring, damper, one mass, one spring, another mass, one spring, another mass, one damper, right, one mass and one spring, mass 1, mass 2, mass 3, mass 4, mass 5. If I ask you what is the order of differential equation here, what's your answer from vibration course? What is that? I mean that is transfer function. Obviously gonna be 5. Obviously gonna be 5. That's right. Understand? So the differential equation of these, okay, so if you have n of these, you're gonna have nth order system. That's right, nth order system. So for general case of yn means nth order time derivative. N can be 2 as we have seen, can be 3, can be 4, can be 5, like this. Y double dot, Y triple dot, Y 4 dot, and that's right, plus it is LTI system, so the coefficients are constant and the system is linear. This plus a n minus 1 y dot decreasing, that's right, plus n y is equal to b dot u n b1 n minus 1 u is the control input to the system, that's right, plus bnu. We typically write by m because m is equal or smaller than n for causal systems, but now let us keep to this notation. What the hell is this? So if I apply the Laplace transform that I told to you by assuming that all initial conditions are 0, means y at initial y dot at time 0 is y double dot at time 0 is y triple dot at time 0 forever to y n at time 0, y n at time 0 is 0, you can expand the transfer function from undergraduate control. You can say that S n ys, right, plus a1 Sn minus 1 in y s plus an minus 1 sys plus an ys is equal to b naught Sn u of s plus bn u of s. So see, so simply from here you can say y of s Sn plus a1 Sn minus 1 plus an minus 1 in s plus an, and the s is what? Frequency variable, is equal to u of s b naught Sn plus finally bn. That's right. So based on the undergraduate control, obviously, right, obviously the output over input of the system, output can be the position of your car, input is the control input, your leg on the gas pedal, okay? As you're pushing that, you're accelerating and your car has velocity and changing the position, okay? Is y of s output over input. U of s is b naught Sn minus 1 plus b1 Sn minus, so this is Sn. Sn minus 1 plus bn. So it is Sn plus a1 Sn minus 1 plus an. So this is transfer function, and we got it. Why? Because we are working on the LTI system. So by having this general form of LTI systems, we have 4 state space representation of transfer function: controllable, observable, observable, diagonal, and the other was, and Jordan form of state space representation. 1, 2, 3, 4. Throughout this course, we're gonna deal many times with the concept of the controllability and observability. Understand? So let me see that what you have here. Okay, so okay, now let me teach you the first one: controllable state space representation of transfer function. By having this in this hand, okay, general form of the LTI systems, this is the general form of controllable system in state space. x dot 1, x dot 2, x dot n minus 1, x dot n. You are writing in the state space form. Look at here. Where is that? State, instead of m, here is x. You understand? Instead of m, here is x. The first column is the m dot 1, m dot 2, m dot 3, m dot n. Here you have x dot 1, x dot 2, x dot n. Is equal to, this is controllable form of state space representation. Here we go. x1, x2, xn minus 1, xn plus u. So I'm gonna freeze it here and back it here, because for those of you that you don't know, I have to teach you here. Guys, look at this equation, right? I can write the left hand side as this, m dot 1 and m dot 2. Yes or no? This is a vector. That's right, it's a vector. 2 by 1. 2 rows and 1 column. Now, this is the state space, linear state space representation. M1 and M2, right? Look at here, guys, in the right hand side. Do you see any M1 here in the first line that I'm naming as F1 and the F2? No, only is M2. So in the first line must be 0, but we do have M2 here, that's right, so 1. So if you multiply this row by this column, you get the same result. M dot 1 is equal to 0, M1. Here we go. Clear? Now look at here. So you have M1, so is minus 1. You have M2 minus 1. Understand? So minus 1 is M minus M1 minus M2 is equal to M dot 2. Plus, but this is the input to the system that I'm showing with you. Okay, with you. That's right. You are designing this course, this control to the system, this controller. So it's gonna be u, because only I have one input to the system. One input to the system. Okay. So this name of the system is CISO. CISO. Single, if you remember from the graduate controller, single input and the single output. CISO system. I'm giving one, I'm pushing the gas pedal, and I expect only the position of the car to be changed. CISO system. So this is you, that's right. Oh, thank you. What is this? Okay, this is you. Do you see any control input here? No, so it's gonna be 0. Do you see any control here? Yes, 1. So now, as I'm gonna teach you, the name of this gonna be A matrix, constant A matrix. This is gonna be B matrix, B matrix, B. Okay. So now I can lump this system by saying that, well, if you look at here, I'm defining M, bold M as vector of M1 and M2. I define it, okay? So you're gonna have, so this is gonna be M dot. So you can write this equation as capital M, bold M, boldface M. M dot is equal to matrix A, and this is boldface M plus vector B in U. So this is a compact version of state space LTI system. State space LTI system. So the same here, when I see that x dot 1, x dot 2, x dot n, this is for the nth order system. This is the nth order system. Right? This is the nth order system. Means that differential equation that you originally had was yn, nth time derivative. So this is the controllable form. How is that? It is 0, 1, 0, continues to 0. 0, 0, 1, 0, second line, first line, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. This line is continuous. This 1 is moving. See? 1, 1, 1, 1, 0. This 1 comes here. And the last line gonna be from this equation, guys. From this equation. Gonna be, I'm reversing the order of the coefficients and multiplying by minus an minus 1 minus an minus 2 and finally minus a1, reversing. Okay, and this is your A matrix. That's right, this is your A matrix as I told. Now the B matrix gonna be 0, 0, oh my god, okay, 0, 0, I mean this is how to move this. Suppose this is 0, that's right, and dot 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 and 0 and 1. The last one is 1. So now you have the controllable form of state space representation. You're going to ask me how? Just you can look at your reference, that is Ogata or any linear system theory books. In the problem problem. Oh, what's happening, guys? Freezing. Okay, problem A, I have no idea. Okay, this is the tablet is warming up, so I have to stop it. But problem A91 of the Ogata book, let me see, yeah, 9, 1. You can find the proof of how we derive the controllable form of state space. I don't want to waste your time with that. Just learn, okay? Okay, so this is the first class. We're going to continue the next forms on the next classes.